Let's start with the good news, and that's what this is. We had a finalized bipod leg, no mistakes. I actually have two of them, but very happy with this. Anything you see will blast out and will get Cerakoted. But it took 4 additional mistakes to get here. I'm not going to bore you with a ton of the detail on those mistakes, but I do want to talk through why each of them was a mistake and how it got there, because it does influence how I was able to, in the end, get to a successful end result. If you've been watching my channel, you have noticed that I bought a Tormach CNC mill. You'll see some of that in just a second. I'm going to spout off some terminology while explaining this, that if you're not used to CNC mills, or Fusion 360 specifically, some of it might seem Greek. So I highly suggest you go and watch that video as well. But first and foremost, this one was my first mistake. And not only did I place, when I flipped it, did I flip it the wrong way? So the little nodule is at the wrong part here. But what we can see is we've got a lot of surface issues, both ends. You can see a lot of just aggressive cuts. And that's also prevalent on the other faces as well. And the reason for that, and I'll show you a picture here of this bipod in the vise on the CNC mill, there was too much sticking out of the vise, and so there was vibration, and we got less than desirable results. But I was able to use this to drill in the end and test my theory on the spring action, and it works great. The second failure, though, after this, I said, okay, I'm going to give up on using a traditional vise. I need to do something else. So I went and created a second pair of dual movable vices to go with my Saunders MachineWorks vise. I modified the plate to fit on the Tormach, and so I started using those. And the first attempt, when I milled it, I thought that if I gripped it all the way up to the hexagons, that wouldn't be too much sticking out and that I wouldn't have a problem. Well, it turns out that was not the case, because I had big problems. And not only did I have vibration problems, which you can see in the surface quality on mostly the chamfers. Everything else was fairly good, but the chamfers were a big problem. The other thing you'll see is that the chamfer on this edge is much larger than on that edge. One thing I learned that I did not expect with those Saunders MachineWorks vices is when you clamp them down, they don't hold tram very well. They will flex up to about 5 to 10 thousandths of an inch. And if you're just clamping a 4-inch piece of something, okay, that's not the end of the world. But that 5 thousandths, 10 thousandths of an inch, over 4 inches now transfers to being a ton over a almost 9.5-inch length bipod leg. And so when I was zeroing things out up here at the head and it pushed, you can see what that ended up as. So that was a hard lesson learned. I therefore started not to trust the tram, and each time I did a setup on everything else, I would get my test indicator out and I would run along the edge to make sure that I was perfectly straight again, and I would actually tighten the clamps on these vices in order to affect the tram and to make sure that it was perfectly straight. That was all well and good, but I thought, okay, maybe if I get my tram correct, I won't have vibration issues with just this sticking out. As we can see, that did not go so well either. Lots of vibration. So I finally caved and said, okay, I need to stop trying to clamp things half-assed, and I need to do a full length, what's called a soft jaw. So you mill it instead of out of steel like a hard jaw, you mill it out of aluminum, but you make the jaw perfectly match the complex geometry of your shapes. And that's how we got this mistake. And this was the worst mistake yet. I have been used to using hard jaws this entire time. And what I learned the hard way was that soft jaws, even when they're perfectly matched to the perimeter of your shape, really cannot handle nearly as much stress on them as a hard jaw clamp can. And so I actually ended up having the 1/4 inch bit that mills this surface here. It's an upcut bit, and it actually pulled it out of the jaws, gouging it and then flinging it across the machine. Not only did it absolutely ruin the part, but it also broke a $30 bit. If you haven't been able to tell yet, this bipod is getting very expensive. Not because it should be, but the learning curve. This really sucked. I almost gave up for the day, but I'm glad I didn't, because what I did is I backed off how much I cut width-wise with each pass with the larger bits, anything above 1/8 of an inch. And that actually led to my final success. And like I said, I've got the other one ready to go as well. But I used to, in hard jaws, be able to cut with a 1/4 of an inch bit at whatever depth I wanted, a 0.1 inch, so almost half its diameter. Not depth of cut, but like width of cut. I had to back it off to 60 thousandths of an inch width of cut so that it wouldn't pull it out of the vise. But we do have success. I'm now going to walk you through the successful bipod. I've got some pictures I'm going to show you, and I'm going to walk you through in the Fusion 360 program the actual paths I used and what the strategy to mill this out looked like. And you might be saying, wow, he cheated. He bought a CNC mill and finished the bipod leg that way instead of finishing it on the hobby CNC that he started on. Yeah, kind of. I bought the mill for a different purpose, but if I have it anyways, why would I not use it? And the other thing that I will say is what I learned from these mistakes on the mill is that the mill actually can be very unforgiving, as you can see here, because it's a very powerful machine in comparison. The other thing that I learned is all of my success didn't have to do with the machine itself. It had to do with fixturing and clamping and reducing vibration. So although I stand by my comment that you're probably not going to get away with using 1/4 of an inch or bigger bits on a hobby mill, a hobby CNC, I still think that you could very easily make one of these legs. You'll probably have some trial and error. If A, you're okay with a little bit of vibration aesthetic or sanding, and B, you don't go over 1/8 of an inch with your bits. But again, all the same rules about quality clamping that applied here are going to apply to a hobby CNC as well. So if you want to try something like this, I would suggest just biting the bullet and wasting the material from the beginning and making a set of soft jaws for the complex shapes that you'll have once you flip your piece over. But let's go look at the success. As you'll see, I originally started by milling the top of the bipod and then milling the bottom of the bipod. That was not a great strategy, so I started a new strategy where I milled the bottom first. The reason for this is if you look at the top of the bipod, there's a lot of different levels. Nothing is coplanar. Whereas if you look at the bottom of the bipod, the only thing that is not coplanar is our little indexing nub. And that is in the center and generally out of the way of clamps. So it's better to mill the back and then flip it over and mill the top, because the back gives you nice flat surfaces to index off for your second operation. All right, what we started doing is we cleared everything out using a 1/4 inch bit except for that nub. I'll show you the feeds and speeds over here so you can get a general idea of what I was working with. 3 flute 1/4 inch bit, clearing out everything except the nub to the desired depth. Yep. And then we did the exact same thing, but we went way deeper. We went all the way down until the minimum amount that I couldn't hold any less than with my Mighty Bites. in the Saunders Machine Works vices. We went down just to above those and did another adaptive path with our 1/4" bit, leaving though this time a 20,000th of an inch radial leftover stock. And that is because we then came down and did a 2D contour that cleared everything up to the actual dimensions of our profile. Those 2D contours, they're not going to be as intelligent on how they remove material, but they will leave a nicer finish for a profile. And so that's why we cleared up everything except for 20 thousandths radially, and then came back and cleared up the rest. We then switched to a 1/8 of an inch bit and used an adaptive clearing path just for all of those corners where I had a tighter radius than my 1/4 of an inch bit allowed for clearing. And then I also used that same 1/8 of an inch bit to adaptive clear our hole that will attach it to the bracket, as well as, again, adaptive clear followed by a 2D path. And then also we did some adaptive clearing for these lightning features on the rear. Again, this is a 3-flute 1/8 of an inch bit. You can see a little bit of information on how I was cutting this and what speeds and feeds I was running. And last but not least, we came back and we did our edge breaks on all of those features, as well as you'll notice here a feature that doesn't exist yet. This is because we're going to mill it from the other side, but I did want an edge break on it. And so we went ahead and just did a chamfer there, even though the feature doesn't exist yet. You'll see what that turns out as in a second. And then last but not least, we came back through and we did our profile chamfer. These were all done with a 4-flute 90-degree chamfer bit. And if you saw my tutorial with the Tormach, you'll understand a little bit better on what I was doing here with tip offset and widths and stuff, and why I didn't model the chamfer. All right, let's now flip it over and see what we're working with. So now we're going to look at milling the top. And I'm also going to turn something on for y'all so that you can see it. This is what the soft jaws look like around that bipod when we clamped it. So we've got the dog bones at all the corners to make sure that we can accommodate their sharpness. And then the soft jaws clamp onto the edge of that. So that's how we did that. But let's talk about it. Again, we're going to work through a very similar pattern. We are going to do adaptive clearing for everything except for what we want left profile-wise. Then we're going to use another adaptive clearing with a 1/4 of an inch bit to leave just our head. And then we're going to take a little bit of facing off the head. The reason for that is this is a 3/8 of an inch thick tool, but the material that I had was 0.380, so I just took that 5/1000 of an inch off here. I just picked a spot to do it. I could have done off the back too. Now, when we look at these pictures, you may see that I actually didn't do it in this particular order. It doesn't actually matter, because as long as you do the 1/4 of an inch bit first and the 1/16 of an inch bit after the 1/8 of an inch bit, the order actually doesn't really matter. So I did my 1/4 of an inch bit, and then I came through and I did all of my chamfers. So we have a 40 thou head chamfer. We now have an 80 thou head chamfer that does just everything except that right front edge. And what was interesting here is that was achieved by playing with open chain geometries, and we chose just part of the head, and that's how we were able to get just that thicker area on those edges. And then followed by our main chamfer for the entire leg, and just a tiny little chamfer here for our screw hole that attaches it to the bracket. Next, I came back and I used my 1/8 of an inch bit to clear out, like I said, all those features, leaving a little bit. I also went ahead and did the deep through slot, and that is the feature that I talked about pre-chamfering on the back edge, even though it didn't exist yet. The reason I did the through hole from the top and not the back is I wanted to try and increase the likelihood that the edges of the through hole and the edges of the non-full depth feature here match up along this edge as well as possible. And so I wanted to do them from the same side, just in case. Then we came through and we went ahead and used a bigger 3/8 of an inch chamfering bit. The reason for that is this is a 1/8 of an inch wide chamfer. And so if I used 1/4 of an inch, I wouldn't have been able to offset the tip of that bit, and you get that rollover edge that we talked over in a previous video. Not nice. So went and bought a bigger bit. There are other ways to do this in multiple steps, but it was just easier for me to do it that way. And then of course we do the same thing on the rear. And then last but not least, I came back at the end and I ran a 1/16 of an inch bit, and I cleaned up the last little both depth as well as axial stock off of all of the features. And because this bit runs so dang slow, that's why I generally run it at the end and out of order from what you see here in the plan, just because I'm constantly changing bits because all this other stuff is fast. And so I just get it out of the way and then I just let this run for, God, I think it was like 10 minutes probably. So that was the strategy, and that was what was successful in the end. The very last thing that we need to do with the bipod legs is to drill our set screw hole at the top. I'm using a 1032 by 1/4 inch set screw, so we are going to start with a number 21 drill bit. What I've done is I've set up a square fence to make sure that we go down square in this direction. I've set up a blocking square as well so that it can't tilt in that direction. So we should be going down straight in 2 axes now, and I do have it clamped, and the little nub at the back that locks into our bracket, those 2 things together are going to keep it from going down in the Z due to the pressure of our drill. I have already measured out, marked, and done like a little divot point in the top to positively index my drill. And when I was setting this up, you can see that little spot. I was pulling the bit down and watching for if it moved when it hit the spot. If it doesn't, we're good. As you saw, I really went slow and steady because I wanted to minimize the risk that the bit would wander as it made its way down to our opening here. I'll have to clean out that swarf from the bit, but we can now get to tapping. I'm going to oil up my tap and just do it by hand with a hand tap. Now what I will say is, besides oiling it, one thing to keep in mind is get a good tap. Remember, this is going on a firearm and it's going to be under a lot of stress. So we want really high quality set screws, and to match that, we want really high quality taps as well. Not all taps are created equal. So for example, if you want a nice high tolerance tap hole for a 1032 set screw like mine, what you're looking for is an H1 tolerance tap. And there we go. We have a tapped hole. I'm going to go a little bit full deep depth. Oh, it's bottoming out, so I guess that's how deep I'm going. Why don't we go ahead and check this hole with our actual pieces that we'll be using. So what we're going to do is we're going to insert the screw that will attach it to the bracket. We will insert our spring with a slightly smaller diameter than the thread that we just did. And last but not least, our 1032 by 1/4 of an inch set screw. Springy. I must be getting good at this stuff because I got miraculously close to being accurate on the first try with this bracket.
Obviously, my problem was right here at the end when I did my final operation. I forgot that my wiggler for setting my y-axis 0 has a diameter to it, and so I put in the wrong value, and it cut further in this direction than it should have. So we got some stuff left over here and some more over here. I could probably hand finish this though and it'd be fine. But we are going to cut a new one, and I'm going to show you the 3-step process this time for getting this bracket with that angled section nice and clean. Just like I did last time with the bipod leg, I'm going to simultaneously run through what I did to accomplish this in Fusion 360 CAM and how that looks with my setup on the actual machine. But the first step is actually going to be to mill the piece as if it sits like that. As you can see, even though I got a decent result my first try and then subsequently success on the second and third tries, it took me 3 strategies to get there. So I actually did more strategizing this time than on the bipod leg itself. But let's roll into this. I'm going to focus on stuff we didn't learn on the bipod, like new tools and bits and what the strategy was. So first and foremost, I started by milling from the top down and using a 3D strategy to give me at least a rough in of my 25-degree angle section. The key here is this set me up for future success where I had to move the part and index it and set my zeros in future setups. And we'll see that in a second. But the key here was, you'll notice that I milled this edge from this top. So this angle here between the face and the edge is not 90 degrees. The reason for that is in my second operation where I do mill straight down and get these pockets at 90 degrees, that acute angle there allowed me to positively register on this edge to set my zeros. And that was really important to me. The other thing that I had to do here that is new is I used the surfaces tool in our design workspace to plug this hole as well as these 5 index holes. That allowed me in this setup to rough it out and then run a parallel path on this face in such a way that it didn't try and dive the tool down into these holes. The reason that was important to me is, remember, I'm going to have to index off of this edge on my next setup, and so if I had even partially roughed out this pocket, I wouldn't have that sharp acute edge to register against. And so that's why that strategy was employed here. So let's take a look at what the roughing 3D path looks like. So running at 37 inches per minute on a 1/4 inch 2-flute ball nose ZR encoded here. Just everything all the way down to the model bottom, but we did do it in steps. And we left some stock to remove as well. And then I came back and did a parallel just on this face because everything else is actually 2-dimensional compared to what the coordinates of this setup are. And the parallel, so the only thing that we changed is what we were cutting, the geometry. We chose just that section and plugged the holes. And then we ran it at a slower pace and had a lower step over and depth of cut. All right, from there, I went ahead and got rid of a lot of material in a 2D manner. I came around and I cleared out the leftovers of my profile so that it's nice and perfectly sharp corners at the bottom. I got the wings nice and flat by selecting just those edges, and so we flattened everything. And then finally I came through with smaller bits and did stuff like the holes, 82-degree countersink. The cool thing here was my countersink is an 1/8 of an inch bit. It wasn't big enough to do that full thing. So instead of just using a 2D chamfer, I actually did a bore path. So it helixes down into that, and that let me use a smaller tool to get that larger path done. And then finally I came through and we did all of our chamfers on the 2 sides and the back
you'll notice that in order to get that done, I had to undo my modeling of my chamfers because that was giving me problems where I, again, could not offset the bit, and that leaves a really poor edge. If you've watched my video on the complete noob's guide to Tormach, I talk about why modeling chamfers leads to lots of problems. So it was nice to be able to undo those chamfers and get really nice edges this way. The interesting thing was when I tried to do this back edge, because of this angle here, it refused to cut that section. So I actually had to do my two sides independently and select just these sections. And then I came back and I actually ignored the model. And for the back edge, I actually selected a line out of the sketch and I used that. And then it started plowing through that section like I asked it to. Don't know why that was the case, but that's what it took. All right, the second setup is pretty interesting. This is where it gets a little complicated because we have to find something to register off of. So I ended up using the tip here for my X, and then as long as we keep the X value consistent across both of these sides, we can actually find the center using the edges of this round, no matter where we are. Because we're just gonna look here, divide by 2, and we're good. And then because this was cut with a 3D path, this face, I couldn't reliably use that as my Z indicator. And so what I know is from my model, this face is actually back here at the same level as my chamfer edge. So I was actually able to use the chamfer edge and my fly cutter to set my 0 for the Z axis. We then milled the hole, and we went ahead and also did a roughing out using this larger bit of those hexagon lock index holes along the edge for our angle indicators. And then I do want to talk about thread milling. Lots of thread mills are very expensive, so I actually taught myself to thread mill using the cheap Chinese stuff. It actually works pretty dang good. For a 1024 hole here, I used a 4.8 millimeter thread mill that I found on Amazon. It does stuff from 5.5 millimeter, quarter of an inch and up, as long as the pitch is 16 to 50 pitch. The interesting thing is a lot of thread mill information that you'll find online, it goes and talks about like flats at the edge of the tip of that thread mill and how you have to do calculations. What I found is these Chinese ones actually don't have a flat at the edge. So I was able to simply use my actual thread pitch and then this pitch diameter offset. It didn't have to change much. So this is where that flat comes into account. The actual pitch diameter offset here is 0.48. So that's taking your major diameter and minor diameter and figuring out what that offset is. I only had to add 1,000th of clearance for the screw to fit in perfectly with a very high tolerance. So there's almost no flat on these thread mills. If that doesn't make sense to you, go watch some videos on thread milling and it will start to, especially the Saunders Machine Works New York CNC stuff. He's really good. And last but not least, we came through with the 1/16 of an inch bit and finished off these index holes to their final dimensions. The 1/16 of an inch bit was necessary to get me my very sharp corners that coincided with the radiuses on our actual bipod leg. For the third setup, we actually end up flipping this upside down, and I was a little bit sketched out when I was first designing this because the bit has to plunge pretty far down to that surface there. So I had to make sure that this whole section that we were working on was actually outside of the jaws, and that only left this section really up to this point to grab onto. So I was a little concerned that I wasn't grabbing onto enough, but it worked out pretty well. Another thing that I did in order to potentially reduce the stresses is I oriented the part in the jaws in such a way that we were doing our cuts mostly moving in the Y direction, so against the jaws instead of with the jaws. So that helped out. And then also you'll see in the pictures, I cut off everything I didn't need on a bandsaw and left just this corner for positive indication. The reason for that is if you leave a lot of overhanging extra material and you come through with your facing mill, which is our first operation here, what ends up happening is when you get really thin, the aluminum wants to curve, and if it curves upwards towards your facing mill, in my case a Superfly, it's gonna want to take more effort to do that cut, because now you're cutting a deeper cut because the aluminum's bent up. It could also cause the face mill to grab the part and throw it if you don't have enough pressure on your jaws. So just any reduction of risk there was a good thing for me. And we also took nice tiny cuts, 20 thousandths at a time. Then I came through and I did similar 3D paths. I did a roughing paths to finish up this bottom section. I did a finishing path to make it nice and smooth. And then the last thing I needed to do was, because of the nature of these bits, they weren't able to get perfectly up against this edge. So I ran a flat bit to finalize against that edge. It's difficult for me to explain just how excited I am to be done with this portion of the project. I significantly underestimated the learning curve that would be presented by this. It was quite hard. While I've said numerous times, I think you could probably get away with making the bipod leg on a more hobby-oriented CNC. I'm not 100% sure that that applies to this piece, the bracket that attaches it to your M-LOK hardware. The reason I say that is just you end up going much deeper on this piece, and if you're not able to get 1/4 of an inch bits to work well on your hobby CNC while cutting a harder material like aluminum, you're really going to struggle. And you're probably going to have to slow things down significantly. You're probably not going to have great surfaces in the areas where you've got to go deep. I think that's the limiting factor. Again, if you're willing to compromise on quality a bit, you might still be able to do it, but I think this is the harder part of the two. So either design it in a different manner that doesn't have that issue, or yeah. Either way, let's talk about the result. I'm very happy with how it came together. The one thing I would change if I did this again is I would have tighter tolerances on this slot here, where the screw holds the two pieces together. It's got a little bit of movement. I believe it has a 10,000ths of tolerance, so 5,000ths on each side of the screw, and that was just a little too much. Now we could lie and call that loading of the bipod, but we all know that I probably should have just made that a little tighter. No way in hell I am cutting this again though, so we're going to live with this. Let's talk about what I don't love about the final result on these. One, because of how I did my strategy, right here at the corners where these two sections meet, you will see that there's a little rounded section because the bits couldn't get in there. That's both the bit that did my profile cut as well as the bit that does the chamfer. So that's a slight imperfection. It's fairly small. I'm more than happy to live with it, but if I wanted to, I could have done another 4th setup like this and come in with a bit and chipped that out real quick. It doesn't bother me enough to actually care about doing that. The second thing is, you can see it's still a slightly rough surface here that will not blast out, and same thing with on the back. It's got a little bit of a bump right here at the end, same here, and that's just because of how those ball nose bits work. So I'm gonna have to do a tiny bit of manual finish work here, or I just sand those two surfaces with 220 on something flat just to knock that little bump out. Not in the world, but it's not a finished part right off the machine. Last but not least, although it ended up with a perfectly viable, usable result, I'm not super happy with the methods that I used for my 2nd and 3rd operation on the bracket. They were a little bit sketchy, but with the tools that I have available to me, and not doing multiple runs of these things, just doing 2 of them and calling it a day. It was good enough for me. It's not going to be aircraft, aerospace, whatever grade tolerances, but we are well within the allowable spec for the purposes here. But if I were to do a large batch of these, I probably would come up with jigs to more accurately and more strongly hold the part for the second and third operation. But as you can see, it works great. You can lock it into the different positions. It holds itself. Tightening this screw truly does change the tension on it a lot. So I'm calling this a big success. Next time you see it, it will be Cerakoted. I'm not sure what color yet. And I'll probably put some sort of plastic Derlin washer in between this and the leg, just so that I can tighten it a little bit more, Loctite it, and it still has the ability to move nice and free. Lastly, let's talk about installing M-LOK parts, because if you've never done it before, it can be a little confusing. We're not going to install it on the actual handguard, because I want to be able to show you what's actually happening behind the scenes here. So we're going to pretend that we are installing this bracket, and that the edge of this wrench is the bottom of the M-LOK slot on our handguard. That's going to allow us to see what's happening internal to the handguard and understand why these M-LOK nuts work. What I like to do is screw the nut on all the way up against the wall of the accessory and then back it off until it's just, parallel. And that allows us to fit it into our imaginary slot. And then from there, I'm going to use whatever method of attachment. This is a hex here. And I'm going to back it off about a half turn and then try moving forward. And you see it's not going to turn when I try and move it forward because it hasn't pushed the wings of the nut far enough to go over the thickness of our handguard in the slot. So now I will go ahead and back it off again about a half and then try and turn forward. And now you see it's just gone far enough that it's going to lock. And the reason that it locks is if we take this back off, the non-winged part of the nut is not a perfect square. It's got a rounded section here and here, and then a squared section here and here. And that allows it, once the wings have cleared the thickness of the handguard, it allows it to turn in this direction, but not turn in that direction past a certain amount. So it'll lock and then stop. It won't let you go past that.